Have you ever looked up at the night sky and wondered about the true scale of the cosmic structure we call home? The Milky Way stretches across the darkness like a river of stars, but what you're seeing represents just a fraction of its true mass. Tonight, we're embarking on a journey to answer one of the most profound questions in astronomy. How massive is the Milky Way? And I mean truly, incomprehensibly massive. We're talking about a galaxy so enormous that it contains hundreds of billions of stars, yet stars make up only a tiny fraction of its total mass. We're diving into a cosmic structure where the visible matter we can see represents less than 1/6 of what's actually there. A galactic giant where dark matter, that mysterious, invisible substance, outweighs everything we can observe by a factor of 5 to 1. If you've ever felt insignificant looking up at the stars, just wait until you grasp the true scale of the galaxy those stars inhabit. Before we embark on this cosmic journey, I'd love to know where you're joining me from tonight. Drop your location in the comments below. There's something beautifully humbling about contemplating the Milky Way's immensity while scattered across our tiny corner of this vast galactic disk. Also, I would be grateful if you consider subscribing or hyping up this video with hype points if you like it. It would mean the world to me. Let's begin. Now, I want you to imagine something for a moment. Picture our sun, that massive ball of nuclear fire that provides all the energy for life on Earth. Got that image in your mind? Good. Now imagine you could somehow gather up 1 trillion suns, each one identical to ours. The combined mass of all those stars would roughly equal the total mass of the Milky Way galaxy. That's right, 1 trillion solar masses. But here's what makes this even more mind-blowing. Despite containing the mass equivalent of 1 trillion suns, only about 60 billion actual stars exist in our galaxy. So where's all that extra mass hiding? The answer leads us into one of the greatest mysteries in modern astronomy. This isn't just another astronomy video where I rattle off some numbers and call it a day. We're going to explore how the Milky Way's massive scale has shaped the evolution of billions of stellar systems, influenced the formation of heavy elements that make up planets and life itself, and continues to act as a cosmic crucible where new stars are born every year. We're going to dive into recent discoveries that suggest the Milky Way is even more massive than we previously thought. With a dark matter halo that extends far beyond the visible disk and exerts gravitational influence across millions of light years. By the end of this journey, you'll understand why the Milky Way isn't just our home galaxy. It's a cosmic structure so massive that it warps space and time itself, bends the fabric of the universe around it, and dominates the gravitational landscape across a region of space larger than most galaxy groups. It's a world unto itself, containing more matter than most galaxies in the observable universe, and it's been growing for over 13 billion years through continuous cannibalization of smaller galaxies. But let's start with the basics, because even the basics about the Milky Way are absolutely mind-blowing. When we talk about the Milky Way's mass, we're not just talking about something that's a bit bigger than a star cluster. We're talking about a scale so vast that it breaks our normal understanding of what a gravitational system should be. The Milky Way's diameter stretches across approximately 100,000 to 200,000 light-years, depending on where you measure the edge. To put that in perspective, light traveling at 186,000 miles per second takes 100,000 years to cross from one side of the galactic disk to the other. If you wanted to drive across the Milky Way at highway speeds, it would take you about 600 trillion years. That's longer than the current age of the universe by a factor of 50,000. But here's where it gets really interesting. The Milky Way isn't a flat disk like you might imagine when you see artistic representations. It's actually a complex three-dimensional structure with multiple components, each contributing to the galaxy's total mass in different ways. We're talking about a central bulge, A thin disk, a thick disk, spiral arms, a stellar halo, and that enormous dark matter halo that extends far beyond anything we can see. Think about that for a moment. This is a structure so large that light from stars on one side of the galaxy hasn't had time to reach stars on the other side since before humans evolved on Earth. And that distance exists not in empty space, but in a region packed with stars, gas clouds, dust, and that mysterious dark matter that dominates the galaxy's gravitational field. Now, if the Milky Way's diameter is 100,000 light-years across, you might think you could calculate its volume using simple geometry. But that's not how galactic structures work. The Milky Way isn't a sphere or even a simple disk. It's a complex spiral structure with density gradients, warped edges, and a thick halo that extends far beyond the visible disk. When astronomers calculate the Milky Way's volume, they're really defining a region of space where the galaxy's gravitational influence dominates over the expansion of the universe itself. This means the Milky Way's volume isn't just about how much space it occupies, it's about how much space it controls through gravity. And that gravitational influence extends across distances measured in millions of light-years, far beyond the visible edge of the galactic disk. The Milky Way weighs in at approximately 1 trillion solar masses. But here's the kicker. If you took all the stars we can actually see in the Milky Way and added them up, you'd only account for about 60 billion solar masses. Add in all the gas, dust, planets, black holes, neutron stars, and every other form of normal matter we can detect, and you might reach 100 to 200 billion solar masses. That's still only 10 to 20% of the galaxy's total mass. Let me repeat that. The Milky Way contains 6 to 10 times more mass in invisible dark matter than in all the stars, planets, and gas clouds combined. This incredible mass concentration exists in a form we cannot see, cannot touch, and barely understand. We know it's there only because of its gravitational effects on the visible matter we can observe. This invisible dark matter happened to accumulate during the early formation of our galaxy over 13 billion years ago, when the universe was just a few 100 million years old. Back then, the cosmos was filled with vast clouds of dark matter that began collapsing under their own gravity, creating gravitational wells that attracted normal matter. The Milky Way began as one of these dark matter concentrations, gradually accumulating hydrogen and helium gas that eventually formed the first generation of stars. But the Milky Way didn't grow smoothly or peacefully. This massive galaxy built itself through violence and cannibalism, consuming dozens of smaller galaxies over billions of years. Each merger added new stars, new gas, and new dark matter to the growing cosmic structure. Some of these ancient collisions can still be detected today in the motions of stars that orbit the galaxy in unusual directions, marking them as immigrants from long-dead satellite galaxies. This process of galactic cannibalism continues today. Right now, as you read these words, the Milky Way is in the process of tearing apart and consuming several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being stretched into a stream of stars that wraps around our galaxy like a ribbon. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are slowly being drawn into the Milky Way's gravitational embrace. In a few billion years, they too will be consumed, adding their mass to our already enormous galaxy. But the Milky Way's mass isn't just impressive as a number on a page. It has real, tangible effects that we can observe and measure. The galaxy's gravity is so strong that it holds together a structure containing hundreds of billions of stars, each moving at hundreds of kilometers per second, yet maintaining coherent orbital patterns that have persisted for billions of years. The Sun itself orbits the center of the Milky Way at a speed of about 220 kilometers per second. That's nearly 500,000 miles per hour. At that incredible velocity, It still takes our solar system approximately 225 million years to complete one orbit around the galactic center. We call this time period a cosmic year. Since Earth formed 4.6 billion years ago, our solar system has completed only about 20 orbits around the galaxy. Think about what that means. The last time our solar system was in its current position relative to the galactic center, dinosaurs ruled the Earth. The time before that, the first reptiles were just beginning to evolve. And the time before that, complex life was just emerging from the oceans. The Milky Way's rotation operates on timescales so vast that entire epochs of Earth's history pass between cosmic landmarks. The Milky Way's gravitational influence extends far beyond just holding stars in orbit. It acts like a cosmic ecosystem, regulating the formation of new stars, recycling heavy elements through stellar death and rebirth, and creating the chemical complexity necessary for planets and life to form. When massive stars explode as supernovae, they scatter heavy elements like carbon, oxygen, iron, and gold into space. These elements eventually incorporate into new generations of stars and planets. Every atom in your body heavier than hydrogen was forged in stars that lived and died within the gravitational embrace of the Milky Way. The galaxy's rotation creates spectacular spiral arms where gas and dust pile up, triggering waves of star formation. These spiral arms aren't fixed structures like the arms of a spinning wheel. Instead, they're density waves, regions where stars and gas temporarily slow down, creating traffic jams that compress gas clouds until they collapse to form new stars. Our solar system passes through these spiral arms periodically as it orbits the galaxy, potentially influencing Earth's climate and the rate of cosmic ray bombardment over geological timescales. But here's something that might surprise you. Despite the Milky Way's enormous mass, most of the galaxy is actually empty space. If you could somehow stand on a planet orbiting a star near the galactic center, where stars are packed most densely, your nearest stellar neighbor would still be several light years away. Even in the densest regions of our galaxy, stars are separated by distances millions of times larger than their own diameters. This emptiness reveals something crucial about the Milky Way's structure. It's not a solid object, but rather a gravitationally bound system of discrete particles, stars, gas clouds, and dark matter, all moving in complex orbital patterns around a common center. The cohesion of this system depends entirely on gravity, that weakest of the fundamental forces operating across distances so vast that light takes thousands of years to traverse them. The Milky Way's mass creates a gravitational field so strong that it affects the very fabric of space and time itself. According to Einstein's theory of general relativity, mass curves spacetime, and the more mass you have, the more pronounced that curvature becomes. The Milky Way's trillion solar masses create a gravitational well so deep that it significantly affects the trajectory of light passing through or near the galaxy. This gravitational lensing effect allows astronomers to detect the Milky Way's mass by observing how it bends light from more distant objects. When light from distant galaxies passes near our galaxy, the Milky Way's gravity acts like a cosmic magnifying glass, bending and distorting that light in predictable ways. By measuring these distortions, scientists can map the distribution of mass in the Milky Way, including the invisible dark matter that dominates the galaxy's gravitational field. But the Milky Way's gravitational influence extends even further than light-bending effects. The galaxy's mass creates what astronomers call a sphere of gravitational influence, a region of space where the Milky Way's gravity dominates over the general expansion of the universe. This sphere extends for approximately 3 million light-years in all directions, encompassing not just our galaxy, but also its satellite galaxies and neighboring galaxies like Andromeda. Within this vast region, The Milky Way's gravity determines the fate of smaller galaxies, gas clouds, and even the cosmic web of dark matter that connects galaxy clusters throughout the universe. Objects within the Milky Way's gravitational sphere are bound to our galaxy, meaning they will eventually merge with it or remain in orbit around it, rather than being carried away by cosmic expansion. The internal structure of the Milky Way is as complex as its size and mass are impressive. At the very center of our galaxy lies Sagittarius A*, a supermassive black hole with a mass approximately 4 million times that of the Sunday. This might sound enormous, and it is by stellar standards, but it represents only a tiny fraction of the galaxy's total mass. The supermassive black hole contains about 0.0004% of the Milky Way's total mass, yet its gravitational influence shapes the orbits of stars in the central light year of the galaxy. Stars near Sagittarius A times move at incredible velocities, some reaching speeds of several percent of the speed of light as they whip around the black hole in highly elliptical orbits. These orbital motions provided the first direct evidence for the black hole's existence and allowed astronomers to calculate its mass with remarkable precision. The fact that stars can orbit so close to such a massive object without being torn apart demonstrates the incredible density gradients that exist at the galaxy's center. Surrounding the central black hole is the galactic bulge, a roughly spherical collection of old stars that extends for thousands of light years around the galactic center. This bulge contains approximately 20 billion solar masses of stars, most of them red giants and other old stellar populations that formed during the early history of the galaxy. The stars in the bulge orbit in complex patterns, some moving in roughly circular orbits around the galactic center, others following highly eccentric paths that carry them far above and below the galactic plane. Beyond the bulge lies the galactic disk, a flattened structure about 100,000 light-years across, but only about 1,000 light-years thick. This is where most of the galaxy's visible mass resides, including our Sun and most of the stars you see when you look up at the night sky. The disk contains approximately 40 to 60 billion solar masses of stars, along with vast quantities of gas and dust that will eventually form new generations of stars. The disk itself isn't uniform, but instead exhibits a spectacular spiral structure, with bright arms of young blue stars and red nebulae marking regions of active star formation. These spiral arms contain enhanced concentrations of gas and dust, compressed by density waves that travel around the galaxy like ripples on a pond. The spiral structure helps organize star formation on galactic scales, creating the stunning patterns we see when we observe spiral galaxies from the outside. Our solar system resides about 26,000 light-years from the galactic center, roughly halfway out to the visible edge of the disk. We orbit within what astronomers call the Orion Arm, a minor spiral feature located between two of the major spiral arms. This location provides us with a relatively stable environment, far enough from the galactic center to avoid the intense radiation and frequent stellar encounters near the core, but close enough to benefit from the steady supply of heavy elements produced by previous generations of stars. But the disk we can see represents only part of the story. Recent observations have revealed that the Milky Way actually has two distinct disk components: a thin disk where most young stars reside, and a thick disk containing older stellar populations. The thick disk extends several thousand light-years above and below the galactic plane and contains stars with different chemical compositions than those in the thin disk, suggesting it formed earlier in the galaxy's history, possibly through the merger of smaller galaxies. Surrounding both disk components is the stellar halo, a roughly spherical distribution of old stars and globular clusters that extends far beyond the visible disk. This halo contains only a small fraction of the galaxy's stellar mass, perhaps 1% or less, but it provides crucial information about the Milky Way's formation history. Many halo stars orbit the galaxy in retrograde directions or on highly inclined orbits, marking them as captured from satellite galaxies that merged with the Milky Way billions of years ago. Beyond the stellar halo lies the vast dark matter halo, an invisible structure that contains most of the galaxy's mass. This dark matter halo extends for hundreds of thousands of light-years beyond the visible edge of the galaxy, perhaps reaching out to nearly 1 million light-years from the galactic center. The dark matter in this halo doesn't emit, absorb, or reflect light, making it completely invisible to traditional telescopes. We know it exists only through its gravitational effects on visible matter. The dark matter halo's mass is approximately 600 billion to 800 billion solar masses, 5 to 6 times more than all the visible matter in the galaxy combined. This invisible mass creates the gravitational framework that holds the galaxy together, providing the additional gravity needed to explain the rotation curves of stars and gas clouds in the outer regions of the galactic disk. Here's where things get really interesting. The rotation curve problem that revealed the existence of dark matter is one of the most important discoveries in modern astronomy. When astronomers measure how fast stars orbit at different distances from the galactic center, they find something unexpected. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just like planets farther from the sun orbit more slowly. But that's not what we observe. Instead, stars in the outer regions of the galactic disk orbit at roughly the same speed as stars closer to the center. Some even orbit faster than Newtonian gravity predicts they should. This flat rotation curve can only be explained if there's much more mass in the galaxy than we can see, distributed in a way that extends far beyond the visible disk. That missing mass is what we call dark matter. The discovery of dark matter through galactic rotation curves revolutionized our understanding of the universe's composition. It revealed that the stars, planets, and gas clouds we can see represent only a small fraction of the total matter in the cosmos. Most of the universe's matter exists in this mysterious dark form, interacting with normal matter only through gravity. The nature of dark matter remains one of the biggest mysteries in physics. Despite decades of searching, scientists haven't directly detected dark matter particles. We don't know what it's made of, how it formed, or why it interacts so weakly with normal matter. Some theories suggest dark matter consists of exotic particles left over from the Big Bang, while others propose modifications to our understanding of gravity itself. The answer could fundamentally change our understanding of physics and the cosmos. But the Milky Way's mass isn't static. The galaxy continues to grow through ongoing mergers with smaller galaxies. Right now, the Milky Way is consuming the Sagittarius dwarf elliptical galaxy, a small galaxy containing several billion stars that is being torn apart by tidal forces. Streams of stars from this doomed galaxy wrap around the Milky Way multiple times, creating stellar rivers that trace the path of the merger over billions of years. The Large and Small Magellanic Clouds, the two most prominent satellite galaxies visible from Earth's southern hemisphere, are also being drawn toward eventual merger with the Milky Way. These irregular dwarf galaxies contain billions of stars each and orbit our galaxy at distances of about 160,000 and 200,000 light-years, respectively. Their gravitational interaction with the Milky Way has already stripped away significant amounts of their gas, creating a vast stream of neutral hydrogen called the Magellanic Stream that stretches across a significant portion of the southern sky. Computer simulations suggest that the Magellanic Clouds will collide with the Milky Way in approximately 2 to 3 billion years, adding their mass to our already enormous galaxy. This merger will trigger massive bursts of star formation as gas clouds collide and compress, potentially creating spectacular displays of stellar birth visible across the galaxy. The merger might also disturb the central supermassive black hole, possibly triggering a period of active galactic nucleus activity that would make the galactic center shine much brighter than it does today. But these relatively small mergers pale in comparison to the cosmic collision that looms in our galaxy's future. The Andromeda Galaxy, our nearest large galactic neighbor, is currently racing toward us at a speed of about 110 kilometers per second. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide in one of the most dramatic events imaginable on cosmic scales. This galactic collision will reshape both galaxies completely. The Milky Way's elegant spiral structure will be disrupted as gravitational forces from Andromeda pull stars and gas clouds into new configurations. Stars will be scattered into different orbits, some flung out into intergalactic space, while others plunge toward the merged center. The combined mass of both galaxies, approximately 2 trillion solar masses, will eventually settle into a new structure, probably an elliptical galaxy that astronomers have already nicknamed Milky Way. Despite the violence of this collision on galactic scales, individual stars will likely pass by each other harmlessly. Stars are so small compared to the distances between them that the probability of actual stellar collisions is extremely low. Our solar system will probably survive the merger intact, though it might be flung into a completely different orbit within the merged galaxy. From Earth, the night sky will change dramatically as the merger progresses, with Andromeda growing larger and larger until it fills much of the sky. The scale of this future collision helps us understand the Milky Way's mass in context. Our galaxy isn't just massive in absolute terms, it's one of the largest galaxies in the local universe. Only Andromeda, among our nearby galactic neighbors, rivals or exceeds the Milky Way's mass. Most of the other galaxies in our local group are dwarf galaxies, containing only a few billion stars each, mere fractions of the Milky Way's mass. This local gravitational dominance means the Milky Way plays a central role in organizing the structure of our corner of the universe. The galaxy's gravity influences the motions of dozens of satellite galaxies, binds together the local group of galaxies, and even affects the distribution of dark matter across millions of light years. The Milky Way isn't just our home. It's a gravitational anchor point that structures the cosmic environment for a significant region of space. But measuring the Milky Way's mass precisely presents enormous challenges. Unlike distant galaxies that we can observe from the outside, we're stuck inside the Milky Way, making it difficult to see the overall structure and mass distribution. It's like trying to map a forest while standing among the trees. We can see individual trees nearby clearly, but understanding the forest's overall shape and extent requires different techniques. Astronomers use multiple methods to estimate the Milky Way's mass, each with its own strengths and limitations. One approach involves measuring the orbital velocities of stars and gas clouds at different distances from the galactic center. By applying the laws of gravity and orbital mechanics, scientists can calculate how much mass must exist within different radii to produce the observed velocities. This method works well for the inner and middle regions of the galaxy, but becomes less reliable at large distances where fewer tracer objects exist. Another technique uses the motions of satellite galaxies and globular clusters that orbit the Milky Way at large distances. These objects act like test particles, their orbits revealing the total mass of the galaxy within their orbital radius. By tracking the positions and velocities of multiple satellites, astronomers can build up a picture of the galaxy's mass distribution extending far beyond the visible disk. Recent studies using data from the Gaia Space Telescope have revolutionized our understanding of the Milky Way's mass. Gaia has measured the precise positions and velocities of over 1 billion stars in our galaxy, providing an unprecedented dataset for studying galactic structure and dynamics. Analysis of Gaia data suggests the Milky Way's total mass within 300,000 light-years of the center is approximately 1.5 trillion solar masses, with significant uncertainty in that number. This mass measurement represents one of the most challenging problems in astronomy because it requires combining observations of visible matter with theoretical models of invisible dark matter. Different research groups using different methods often arrive at somewhat different mass estimates, ranging from about 700 billion to 2 trillion solar masses. The uncertainty arises partly from the difficulty of measuring distances and velocities accurately, and partly from our incomplete understanding of dark matter's distribution. The shape of the dark matter halo adds another layer of complexity to mass measurements. Is the halo spherical, or does it follow a more elongated shape? Does the dark matter density decrease smoothly with distance from the galactic center, or are there clumps and substructures? These questions affect how we interpret observations and calculate the total mass, leading to systematic uncertainties in our mass estimates. Recent computer simulations of galaxy formation suggest that dark matter halos should contain numerous small clumps or subhalos, remnants of smaller dark matter concentrations that merge to form the main halo. If these subhalos exist, they could affect the orbits of stars and satellite galaxies in detectable ways, providing new methods for mapping the dark matter distribution and refining mass estimates. The composition of the Milky Way's mass tells a fascinating story about cosmic evolution. Approximately 5 to 10% of the galaxy's mass exists in the form of stars, those nuclear furnaces that dominate our view of the night sky. Another 10 to 15% consists of gas, primarily hydrogen and helium, distributed throughout the galactic disk and halo. This gas represents the raw material for future star formation and continues to fall into the galaxy from the intergalactic medium. A small fraction, perhaps 1%, exists in the form of dust, rocky planets, asteroids, comets, and other solid bodies. This includes Earth and everything on it, all the planets orbiting all the stars in the galaxy, and every asteroid and comet scattered throughout interstellar space. Despite seeming significant from our perspective, all this solid matter represents just a tiny fraction of the galaxy's total mass budget. Black holes, neutron stars, white dwarfs, and other stellar remnants contain perhaps another % or 2 of the galaxy's mass. These dead stars represent the end products of stellar evolution, the collapsed cores left behind after stars exhaust their nuclear fuel. The central supermassive black hole, despite its impressive 4 million solar mass weight, contributes only a negligible amount to the total. All of this normal matter, everything that interacts with light and can be detected by traditional astronomical techniques, adds up to only 15 to 20% of the galaxy's total mass. The remaining 80 to 85% exists as dark matter, that mysterious substance that reveals itself only through its gravitational influence. This mass composition has profound implications for understanding how galaxies form and evolve. The dark matter provides the gravitational scaffolding that allows galaxies to form in the first place. Without dark matter's extra gravity, the normal matter in the universe wouldn't have been able to collapse into the dense structures we observe today. Galaxies as we know them simply wouldn't exist. The interplay between normal and dark matter drives the evolution of galactic structures over cosmic time. Dark matter halos merge and grow through gravitational interactions, creating larger and larger gravitational wells that attract normal matter. This normal matter falls into the dark matter potential wells, heats up through compression, cools through radiation, and eventually forms stars. The stars produce heavy elements through nuclear fusion and supernova explosions. enriching the interstellar medium with the building blocks of planets and life. This cosmic recycling process has been operating in the Milky Way for over 13 billion years, gradually converting the primordial hydrogen and helium from the Big Bang into the complex mix of elements we observe today. Every generation of stars produces more heavy elements, increasing the metallicity of the interstellar medium and enabling the formation of more complex structures like rocky planets. The Milky Way's mass has also shaped the galaxy's role in the cosmic web, that vast network of dark matter filaments that connect galaxy clusters across the universe. Our galaxy resides in a relatively quiet backwater of the cosmic web, part of a small galaxy group called the local group, rather than a large galaxy cluster. This location provides a relatively stable environment where galaxies can evolve without the disruptive effects of frequent mergers and strong gravitational interactions that occur in denser regions of the universe. The local group itself is gravitationally bound, with the Milky Way and Andromeda as its two dominant members. The combined mass of these two galaxies, approximately 2 trillion solar masses, creates a gravitational potential well deep enough to hold together several dozen smaller galaxies scattered across a region about 10 million light-years in diameter. Without the Milky Way's substantial mass contribution, the local group would look very different, possibly consisting of many more small galaxies that aren't gravitationally bound into a coherent structure. But the Milky Way's massive scale extends beyond just its gravitational effects. The galaxy's total mass determines its ability to retain gas that has been heated by supernovae and stellar winds. Smaller galaxies often lose significant amounts of gas through these feedback processes, as the energy from stellar explosions can accelerate gas to escape velocity. The Milky Way's deep gravitational potential well makes it much harder for gas to escape, allowing the galaxy to retain most of its gas and continue forming stars for billions of years. This gas retention capacity means the Milky Way has been able to maintain steady star formation throughout most of its history. Current observations suggest our galaxy produces new stars at a rate of about 1 to 3 solar masses per year. This might not sound like much, but over the galaxy's 1-3 billion year history, this steady star formation has produced the approximately 200 to 400 billion stars we observe today. The Milky Way's star formation history reveals periods of intense activity punctuated by quieter epochs. Major mergers with satellite galaxies trigger bursts of star formation as gas clouds collide and compress, creating waves of stellar birth that can temporarily increase the star formation rate by factors of 10 or more. The stellar populations we observe today carry chemical signatures of these ancient star formation episodes, allowing astronomers to reconstruct the galaxy's merger history by studying the ages and compositions of different stellar groups. The most recent major merger event occurred approximately 10 billion years ago when a large satellite galaxy called Gaia Enceladus collided with the Milky Way. This merger delivered enormous quantities of gas and stars to our galaxy, triggering intense star formation and depositing stars throughout the galactic halo. Evidence for this ancient collision was discovered only recently through analysis of Gaia data, which revealed populations of stars moving in unusual orbits characteristic of merger debris. The chemical evolution of the Milky Way provides another window into understanding the galaxy's mass and formation history. The first generation of stars formed from nearly pure hydrogen and helium, the only elements produced in significant quantities by the Big Bang. These population 3 stars, as astronomers call them, have never been directly observed because they all died billions of years ago, but their existence is inferred from theoretical models of early star formation. When these first massive stars exploded as supernovae, they scattered newly created heavy elements into the interstellar medium. Subsequent generations of stars formed from gas enriched with these heavy elements, gradually increasing the metallicity of the galaxy over time. Today, stars forming in the galactic disk contain about 2% heavy elements by mass, a dramatic increase from the essentially zero metallicity of the first stellar generation. This chemical enrichment process depends critically on the galaxy's mass. More massive galaxies retain their enriched gas more effectively and experience higher star formation rates, leading to faster chemical evolution. The Milky Way's mass places it in a sweet spot where chemical enrichment has proceeded at a pace that allowed rocky planets like Earth to form with enough heavy elements to build solid structures, but not so fast that all the gas was exhausted before our solar system could form. The distribution of heavy elements throughout the galaxy isn't uniform. Stars near the galactic center tend to be more metal-rich than stars in the outer disk, reflecting the higher star formation rates and more efficient chemical enrichment in the inner galaxy. This metallicity gradient provides clues about how the galaxy assembled itself over cosmic time and how gas flows throughout the galactic disk. Recent observations have discovered stars in the galactic halo with extremely low metallicities, some containing only 1/1,000,000th the heavy element content of the Sunday. These ultra-metal-poor stars represent some of the oldest stars in the galaxy, formed when the Milky Way was young and chemical enrichment had barely begun. Studying these ancient stellar fossils provides direct information about conditions in the early galaxy and the properties of the first generations of stars. The Milky Way's spiral structure, one of its most visually striking features when observed from outside our galaxy, is actually a manifestation of the galaxy's massive scale and rotation. Spiral arms form through density wave theory, a mechanism where gravitational perturbations create regions of enhanced density that rotate around the galaxy more slowly than the stars themselves. As stars and gas clouds enter these density waves, they slow down and pile up, creating the bright spiral arms we observe. This spiral structure helps organize star formation on galactic scales. The compression of gas, as it enters spiral arms, triggers the collapse of molecular clouds, leading to waves of star formation that march around the galaxy following the spiral pattern. The brightest, most massive stars formed in these regions have short lifetimes of only a few million years, so they die while still near their birth sites in the spiral arms. This creates the distinctive appearance of spiral arms traced out by bright blue stars and red emission nebulae. The spiral pattern itself isn't fixed, but rather rotates at a different rate than the stars, a phenomenon called spiral pattern speed. This differential rotation means that different stars pass through the spiral arms at different times during their orbits around the galaxy. Our solar system passes through a spiral arm approximately once every few 100 million years, potentially exposing Earth to increased cosmic ray flux during these passages. Some scientists have proposed that these periodic passages through spiral arms might correlate with extinction events in Earth's fossil record, though this hypothesis remains controversial. The increased cosmic ray flux during spiral arm passages could affect Earth's climate and biosphere, potentially triggering periods of environmental stress that lead to mass extinctions. However, the evidence for such correlations is weak, and many other factors influence Earth's climate over geological timescales. The Milky Way's mass also determines its place in the hierarchy of galactic structures. Galaxies aren't randomly distributed throughout the universe, but instead form clusters and groups connected by vast filaments of dark matter. The largest structures in the universe, galaxy superclusters, contain thousands of galaxies spread across hundreds of millions of light-years. The Milky Way resides in the local group, which is part of the much larger Virgo supercluster, a structure containing thousands of galaxies spread across about 110 million light-years. Even this enormous structure is just one component of an even larger structure called Laniakea, a supercluster of galaxies containing the mass of about 100,000 large galaxies like the Milky Way. The gravitational pull of these large-scale structures influences the motion of galaxies across cosmic distances. The Milky Way, along with the rest of the local group, is being pulled toward the Virgo cluster at speeds of several hundred kilometers per second. This motion, combined with the overall expansion of the universe, creates complex patterns of galactic velocities that reveal the distribution of mass on the largest observable scales. Understanding the Milky Way's mass in this larger cosmic context helps us comprehend how structure formation proceeds in the universe. The galaxy's formation and growth occurred within a specific environment determined by the distribution of dark matter on scales far larger than the galaxy itself. The Milky Way occupies a particular niche in the cosmic hierarchy, large enough to be a significant gravitational structure, but small enough to be influenced by the larger-scale gravitational landscape. Recent advances in computational power have allowed astronomers to create detailed simulations of galaxy formation that reproduce many observed properties of the Milky Way. These simulations start with the distribution of dark matter in the early universe and follow its evolution through billions of years of cosmic time, tracking how dark matter halos merge and grow, how gas falls into these halos and forms stars, and how feedback from supernovae and active galactic nuclei affects the process. The most sophisticated simulations can now reproduce galaxies that look remarkably similar to the Milky Way, with disk structures, spiral arms, bulges, and realistic star formation histories. Comparing these simulated galaxies to observations helps constrain models of galaxy formation and evolution, testing our understanding of the physical processes that shape galactic structures. One surprising result from these simulations is that Milky Way-like galaxies are relatively rare. Most galaxies of similar mass in simulations look quite different from our galaxy, suggesting that the Milky Way's specific combination of properties, its spiral structure, relatively quiet merger history, and moderate star formation rate, represents a somewhat unusual evolutionary path. This rarity has implications for understanding the prevalence of habitable planets in the universe. If Milky Way-like galaxies are uncommon, and if such galaxies provide particularly favorable environments for the development of habitable planetary systems, then potentially habitable planets might be rarer than we'd estimate by simply counting the total number of planets in the universe. The Milky Way's relatively quiet location in the cosmic web, away from major galaxy clusters, may have been important for allowing stable planetary systems to form and evolve. Galaxies in dense cluster environments experience frequent close encounters with other galaxies, tidal stripping of gas, and environmental effects that could disrupt planetary systems or strip galaxies of the gas needed for ongoing star formation. The mass of dark matter in the Milky Way's halo also affects the rate of dark matter particle interactions that might occur in our solar system or on Earth. If dark matter consists of weakly interacting massive particles, or WIMPs, as many theories predict, then millions or billions of these particles pass through every square centimeter of Earth every second. Despite this enormous flux, dark matter particles interact so weakly with normal matter that detecting even a single interaction requires enormous detectors and years of observation. Several experiments around the world are attempting to directly detect dark matter particles by looking for the tiny amount of energy deposited when a dark matter particle collides with an atomic nucleus. These experiments must be conducted deep underground to shield them from cosmic rays and other backgrounds that could mimic a dark matter signal. So far, no experiment has definitively detected dark matter particles, placing increasingly stringent constraints on the properties these particles must have. The local dark matter density in our solar system's neighborhood, determined by the galaxy's overall mass distribution, affects the expected rate of dark matter interactions in these detectors. More precise measurements of the Milky Way's mass and dark matter distribution help researchers predict how many dark matter interactions they should expect to detect, informing the design of future experiments and the interpretation of results. The Milky Way's mass also influences the formation and evolution of its satellite galaxies. These small galaxies orbit within the Milky Way's dark matter halo, experiencing tidal forces that can strip away their gas and even their stars. Many of the Milky Way's satellite galaxies show signs of tidal disruption, with elongated shapes and stellar streams marking the path of material pulled away by the host galaxy's gravity. The number of satellite galaxies orbiting the Milky Way provides information about the structure of the dark matter halo on small scales. According to standard dark matter theories, the Milky Way's halo should contain hundreds or even thousands of small dark matter subhalos, remnants of smaller dark matter clumps that merge to form the main halo. Most of these subhalos shouldn't contain any stars, making them invisible, but some should have captured enough gas to form small dwarf galaxies. Observations reveal only about 60 known satellite galaxies around the Milky Way, far fewer than the thousands predicted by some models. This discrepancy, known as the missing satellites problem, has puzzled astronomers for years. Possible solutions include the idea that many small subhalos failed to form stars and remain dark, that our searches haven't been sensitive enough to detect the faintest satellites, or that our models of dark matter structure formation need revision. Recent surveys using improved observational techniques have discovered dozens of new ultra-faint dwarf galaxies orbiting the Milky Way, galaxies so dim that they contain only a few thousand stars each. These discoveries suggest that many more satellites remain to be found, potentially resolving the missing satellites problem. However, it's still unclear whether the total number of satellites will match theoretical predictions. The mass of the Milky Way continues to be refined as new observational data becomes available and new analysis techniques are developed. The Gaia Space Telescope is revolutionizing our understanding of the galaxy's structure and dynamics by measuring precise positions and velocities for over 1 billion stars. Future releases of Gaia data will include measurements for even more stars, extending to greater distances and allowing more accurate mass estimates. Ground-based surveys are also contributing to our understanding of the Milky Way's mass. Large spectroscopic surveys like APOGEE and GALA measure detailed chemical compositions for hundreds of thousands of stars, providing information about the galaxy's chemical evolution and formation history. Combining these chemical measurements with Gaia's precise positions and velocities allows astronomers to identify distinct stellar populations and trace the galaxy's assembly history. Radio observations of neutral hydrogen gas throughout the galactic disk reveal the distribution of gas that will form future generations of stars. The rotation curve derived from these observations provides one of the best constraints on the galaxy's total mass within the disk region. New radio telescopes with improved sensitivity are extending these measurements to greater distances, probing the mass distribution in the outer regions of the galaxy where dark matter dominates. The study of the Milky Way's globular clusters, dense balls of ancient stars orbiting in the galactic halo, provides another window into understanding the galaxy's mass. These clusters orbit at distances ranging from a few thousand to over 300,000 light-years from the galactic center. Their orbital velocities, combined with their positions, allow astronomers to trace the gravitational potential of the galaxy at large distances where dark matter dominates the mass budget. Recent discoveries of hypervelocity stars, objects moving so fast that they will eventually escape the galaxy entirely, provide yet another method for measuring the Milky Way's mass. These rare stars were probably accelerated to their extreme velocities through close encounters with the supermassive black hole at the galactic center, or through binary star interactions that went awry. Their escape velocity depends on the galaxy's total mass, so observations of hypervelocity stars can place constraints on mass measurements. The Milky Way's massive scale has shaped not just the physical structure of the galaxy, but also the chemical and dynamical evolution that has created the conditions for life. The steady accumulation of heavy elements over billions of years of star formation has enriched the interstellar medium with the building blocks needed for rocky planets. The relatively stable galactic environment, determined partly by the galaxy's mass and location in the cosmic web, has allowed planetary systems to evolve without excessive disruption from close encounters or environmental effects. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust enriched by previous generations of stars. That cloud contained just the right mix of elements to form a star like the Sun, rocky planets like Earth, and the complex organic molecules that eventually gave rise to life. This chemical composition was determined by billions of years of stellar nucleosynthesis and chemical evolution within the Milky Way, processes that depend critically on the galaxy's mass and structure. The location of our solar system within the galaxy also matters. We orbit at a distance where the gravitational environment is relatively stable, far from the intense radiation and frequent stellar encounters near the galactic center, but close enough to benefit from the steady enrichment of heavy elements. This galactic habitable zone, analogous to the habitable zone around individual stars, may represent the regions of the galaxy most conducive to the development of complex life. The Milky Way's ongoing evolution will continue to shape the galactic environment for billions of years to come. The steady accretion of gas from the intergalactic medium will fuel continued star formation, gradually consuming the remaining gas reservoir. The ongoing consumption of satellite galaxies will add new stars and gas to the main galaxy, potentially triggering bursts of star formation in the process. The approaching collision with the Andromeda Galaxy will represent the most dramatic event in the Milky Way's future evolution. This merger will completely reshape both galaxies, mixing their stellar populations and potentially triggering enormous bursts of star formation as gas clouds collide. The combined galaxy will have a mass approaching 2 trillion solar masses, making it one of the largest galaxies in the local universe. Despite the violence of this collision on galactic scales, life in the solar system might survive relatively unscathed. Stars are separated by such vast distances that actual collisions between stars will be extremely rare. Our solar system might be scattered to a different orbit within the merged galaxy, but the Sun and planets will probably survive intact. From Earth, the night sky will look dramatically different, with the merged galaxy's stars scattered across a much larger volume of space. The timescale of the Andromeda collision, approximately 4 to 5 billion years in the future, is comparable to the remaining lifetime of the Sun as a main sequence star. By the time the merger occurs, the Sun will be approaching the end of its hydrogen-burning phase and beginning its evolution toward becoming a red giant. These parallel evolutionary timescales mean that the far future of our solar system will be shaped by both stellar evolution and galactic dynamics. Understanding the Milky Way's mass helps us place our galaxy in the context of cosmic evolution. The galaxy represents a typical massive spiral galaxy, similar to billions of other galaxies scattered throughout the observable universe. Studying the Milky Way in detail provides insights into galactic processes that occur throughout the cosmos, from star formation and chemical evolution to the role of dark matter in structure formation. The Milky Way also serves as a laboratory for testing theories of gravity and cosmology. The distribution of matter in the galaxy, the shapes of stellar orbits, and the dynamics of satellite galaxies all provide tests of our understanding of how gravity operates on galactic scales. Any deviations from predictions could indicate new physics or modifications to our gravitational theories. The question of the Milky Way's mass ultimately leads us to deeper questions about the nature of the universe itself. What is dark matter, and why does it outweigh normal matter by such a large factor? How do galaxies form and evolve in the cosmic web? What role do massive galaxies like the Milky Way play in the large-scale structure of the universe? These questions touch on some of the most fundamental issues in physics and astronomy. As we continue to explore the Milky Way's massive scale through increasingly sophisticated observations and theoretical models, we're not just learning about one galaxy. We're uncovering the fundamental processes that govern galaxy formation and evolution throughout the universe. The Milky Way provides a detailed view of galactic physics that we can't achieve for any other galaxy, making it one of the most important objects in astronomy. Every new measurement of the galaxy's rotation curve, every discovery of a new satellite galaxy, every chemical analysis of ancient stars adds another piece to the puzzle of how the Milky Way assembled itself from the primordial matter of the early universe. This ongoing detective work combines observations across the electromagnetic spectrum, from radio waves to gamma rays, with theoretical modeling and computer simulations. The study of the Milky Way's mass connects to virtually every area of astronomy and astrophysics. Understanding the galaxy's structure and composition requires knowledge of stellar evolution, interstellar medium physics, cosmology, and even particle physics. The galaxy serves as a crossroads where multiple areas of scientific inquiry meet, making it a uniquely rich subject for study. Future observations will continue to refine our understanding of the Milky Way's mass and structure. New telescopes coming online in the next decade will provide unprecedented views of the galaxy's stars, gas, and dust. Space-based observatories will map the distribution of matter with ever greater precision. Computer simulations will become more sophisticated, incorporating more detailed physics and allowing more direct comparisons with observations. The Gaia mission will continue releasing data for several more years, eventually providing precise positions and velocities for nearly 2 billion stars. This dataset will revolutionize our understanding of galactic structure and dynamics, allowing astronomers to trace stellar streams from disrupted satellite galaxies, identify distinct stellar populations, and measure the galaxy's gravitational potential with unprecedented precision. Ground-based facilities like the Vera Rubin Observatory will discover millions of new variable stars, asteroids, and transient objects, providing new probes of galactic structure. Large spectroscopic surveys will measure chemical compositions for millions of stars, tracing the galaxy's chemical evolution in unprecedented detail. Radio telescopes will map the distribution of hydrogen gas throughout the galaxy and beyond, revealing the reservoir of material for future star formation. The James Webb Space Telescope is already providing new views of star-forming regions and the galactic center, revealing details of stellar birth and evolution that were invisible to previous instruments. Future space telescopes will extend these observations, potentially detecting the first generations of stars in the Milky Way's history and probing the conditions in the early galaxy. All of these observations will contribute to an increasingly complete picture of the Milky Way's mass, structure, and evolution. Yet fundamental questions will remain. The nature of dark matter, the detailed history of the galaxy's assembly, and the complex interplay between star formation, feedback, and chemical evolution all represent active areas of research that will continue for decades to come. The Milky Way's massive scale ultimately reminds us that we inhabit a vast and ancient structure whose evolution spans most of cosmic history. The galaxy began forming within a few 100 million years after the Big Bang and has been growing and evolving ever since. Every atom in our bodies was forged in stellar furnaces within this galactic structure, processed through multiple generations of stars that lived and died over billions of years. The chemical elements that make up Earth, carbon and oxygen and iron and gold, were created in supernovae that exploded within the Milky Way's gravitational embrace. The Sun and Solar System formed from gas enriched by these previous stellar generations, inheriting a chemical legacy that spans the galaxy's history. In a very real sense, we are products of the Milky Way's long evolutionary journey, cosmic recycling made manifest in living form. This connection between galactic evolution and the existence of life highlights the importance of understanding the Milky Way's mass and structure. The galaxy's properties, its mass, its chemical evolution, its star formation history, all contributed to creating the conditions that allowed life to develop on Earth. Had the galaxy's mass been significantly different, had its merger history followed a different path, the conditions in our corner of the cosmos might have been very different. The study of the Milky Way's mass represents one of the grand challenges in astronomy, connecting observations of individual stars to the structure of dark matter halos extending across millions of light years. It requires synthesizing information from multiple wavelengths of light, combining theoretical models with observations, and pushing the boundaries of both observational techniques and computational methods. As we peer deeper into the Milky Way's massive structure, we're really exploring the fundamental question of how matter organizes itself in the universe. From the quantum interactions that govern atomic physics to the cosmic web of dark matter filaments connecting galaxy clusters, the Milky Way embodies physical processes operating across the full range of scales in the cosmos. The galaxy's mass creates gravitational fields, shapes the orbits of billions of stars, and determines the fate of gas clouds and satellite galaxies across a vast region of space. This gravitational influence has been operating for over 13 billion years, shaping the evolution of our cosmic neighborhood throughout most of the universe's history. When we contemplate the Milky Way's massive scale, we're contemplating the fundamental forces that govern the cosmos. Gravity, the weakest of nature's fundamental forces, becomes the dominant influence on cosmic scales, shaping structures from individual stars to galaxy superclusters. The interplay between gravity and the expansion of the universe determines which objects remain gravitationally bound and which are carried away by cosmic expansion. The dark matter that dominates the Milky Way's mass budget represents one of the great unsolved mysteries of modern physics. Despite comprising most of the universe's matter, we know almost nothing about dark matter's fundamental nature. Whether it consists of exotic particles, modifications to gravity, or something entirely unexpected remains to be determined. Solving this mystery will require combining astronomical observations of structures like the Milky Way with particle physics experiments and theoretical advances. The Milky Way's ongoing cannibalization of smaller galaxies demonstrates that galaxy evolution is a violent and dynamic process. The galaxy we see today is the product of countless mergers and accretion events that have occurred over billions of years. Many of the stars in the galactic halo were born in other galaxies before being captured by the Milky Way's gravity. Even our Sun might have formed in a small cluster that was later dispersed, scattering its stars throughout the galaxy. This violent history contrasts with the apparent serenity of the night sky. When we look up at the Milky Way stretching across the darkness, we see a seemingly peaceful band of light. Yet this structure contains evidence of ancient collisions, ongoing mergers, and dynamic processes operating on timescales ranging from microseconds to billions of years. The mass of the Milky Way determines its ultimate fate. Current measurements suggest the galaxy will continue growing through mergers with smaller satellites for billions of years before eventually colliding with Andromeda. The merged galaxy will likely remain gravitationally bound as a single structure rather than flying apart, because the combined mass creates a gravitational well deep enough to hold the system together despite the violence of the collision. Far in the future, trillions of years from now, the merged Milky Way galaxy will exist in a universe that looks very different from today. The expansion of the universe will have carried distant galaxy clusters beyond our cosmic horizon, making them permanently invisible. The Milky Way galaxy might be the only large galaxy visible in the night sky, surrounded by darkness as the rest of the universe recedes beyond reach. But these cosmic timescales far exceed the lifetime of stars like the Sunday. Long before the far future arrives, all the stars currently visible in the night sky will have burned out, leaving behind white dwarfs, neutron stars, and black holes. New generations of stars will have formed and died, continuing the cosmic cycle of stellar birth and death that has operated in the Milky Way for billions of years. Understanding the Milky Way's mass helps us understand our place in this vast cosmic structure. We orbit a typical star in a typical region of a large galaxy, participants in a cosmic story that began billions of years ago and will continue for billions of years to come. The atoms in our bodies have been part of this story since the early days of the galaxy, cycling through generations of stars before eventually assembling into the complex structures that make up living things. The Milky Way's massive scale encompasses not just physical dimensions, but also the scope of cosmic evolution, the complexity of gravitational dynamics, and the mystery of dark matter. Every new observation adds to our understanding, yet fundamental questions remain. The galaxy continues to surprise us with unexpected discoveries, from new satellite galaxies to unusual stellar populations to previously unknown structures in the dark matter halo. As our observational techniques improve and our theoretical understanding deepens, we're gradually assembling a more complete picture of the Milky Way's true nature. Yet each answer raises new questions. How did the first stars form in the galaxy's dark matter halo? What triggered the major merger events that shaped the galaxy's history? How common are Milky Way-like galaxies in the broader universe? These questions drive ongoing research programs using telescopes around the world and in space. Every clear night, astronomers are collecting new data about the Milky Way's stars, gas, and structure. Every day, theorists are running simulations to test models of galaxy formation and evolution. The accumulated effort of thousands of researchers over many years is gradually revealing the Milky Way's secrets. The mass of the Milky Way ultimately represents more than just a number or a measurement. It represents the culmination of 13 billion years of cosmic evolution, the result of countless physical processes operating across vast scales of space and time. It represents the gravitational framework that has shaped our cosmic environment and made possible the existence of stars, planets, and life. When we ask how massive the Milky Way is, we're really asking about the fundamental structure of the universe we inhabit. We're exploring the nature of matter and gravity, the evolution of cosmic structure, and the long history that connects the Big Bang to the present day. The answer encompasses visible stars and invisible dark matter, violent mergers and gradual evolution, observed facts and unsolved mysteries. So there you have it. The Milky Way isn't just massive. It's not even just incomprehensibly, mind-bendingly enormous. The Milky Way is the cosmic home that has sheltered our solar system for over 4 billion years. The gravitational structure that has shaped the evolution of matter across billions of light years, and the ancient system whose long history has created the chemical elements and conditions necessary for life. Tonight, when you look up at that luminous band stretching across the night sky, remember that you're not just looking at distant stars. You're looking at a trillion solar mass structure that extends far beyond what you can see, a system dominated by invisible dark matter shaped by billions of years of evolution. and destined to merge with its neighbor in the distant future. You're looking at your galactic home, the massive structure that makes everything else in your cosmic neighborhood possible. The Milky Way's story is our story, the long epic of cosmic evolution that has led from the Big Bang to the present moment. Understanding the galaxy's mass helps us understand this story, connecting the largest scales of cosmic structure to the smallest details of our existence. In the Milky Way's massive presence, we see reflected the creative power of gravity and time, operating across billions of years to transform primordial matter into the complex and beautiful structure we call home. But let's dive even deeper into what this massive scale means for our understanding of the cosmos. The Milky Way's gravitational influence doesn't stop at its visible boundaries or even at the edge of its dark matter halo. The galaxy's mass creates ripples in the fabric of space-time that extend across the entire local group and beyond, affecting the motion of every galaxy within tens of millions of light-years. Consider the gravitational dance between the Milky Way and Andromeda. These two massive galaxies, separated by 2.5 million light-years, have been gravitationally bound to each other for billions of years. Their mutual attraction has been drawing them together throughout most of cosmic history, a slow-motion collision that will culminate in their merger approximately 4 to 5 billion years from now. The combined mass of these two galaxies dominates the gravitational landscape of the local group, determining the fate of every smaller galaxy in our cosmic neighborhood. The mass of the Milky Way can be understood through multiple lenses, each revealing different aspects of the galaxy's nature. From a purely gravitational perspective, the galaxy's mass represents the total amount of space-time curvature it creates. Einstein's general relativity tells us that mass warps the geometry of space and time, and the Milky Way's trillion solar masses create a gravitational well so deep that it fundamentally shapes the structure of space across millions of light-years. This space-time curvature isn't just a theoretical concept. It has real, measurable effects that we can observe. Light from distant quasars passing near the Milky Way gets bent by the galaxy's gravitational field, creating subtle distortions in the apparent positions of these distant objects. By measuring these gravitational lensing effects, astronomers can map the distribution of mass in the galaxy, including the invisible dark matter that dominates the mass budget. The peculiar velocities of nearby galaxies provide another window into understanding the Milky Way's mass. These galaxies aren't just moving away from us due to cosmic expansion. They also have additional motions caused by gravitational interactions with the Milky Way and other nearby massive structures. By measuring these peculiar velocities and modeling the gravitational forces that produce them, astronomers can estimate the total mass of the Milky Way and map its gravitational influence across the local group. Recent studies using this technique have revealed something surprising. The Milky Way's gravitational influence extends much farther than previously thought, affecting the motions of galaxies at distances approaching 3 million light-years. This extended sphere of influence suggests that the galaxy's dark matter halo might be even more massive than current estimates indicate, potentially containing up to 2 trillion solar masses when measured at these large distances. The nature of dark matter itself remains one of the greatest puzzles in modern physics. Despite comprising 85% of the Milky Way's mass, we know almost nothing about what dark matter actually is. It doesn't emit, absorb, or reflect electromagnetic radiation of any kind, making it completely invisible to traditional astronomical observations. Dark matter particles don't interact with normal matter through the electromagnetic force or the strong nuclear force, only through gravity and possibly the weak nuclear force. This extreme weakness of dark matter interactions makes it incredibly difficult to detect. Dozens of experiments around the world have been searching for direct evidence of dark matter particles for decades, using ever more sensitive detectors placed deep underground to shield them from interfering cosmic rays. These experiments look for the tiny amount of energy deposited when a dark matter particle collides with an atomic nucleus in the detector, events so rare that they might occur only a few times per year, even in detectors containing tons of target material. So far, no experiment has definitively detected dark matter particles, though several have reported tantalizing hints that remain unconfirmed. The lack of detection has ruled out many proposed dark matter candidates and placed increasingly stringent constraints on the properties these particles must have. If dark matter consists of weakly interacting massive particles, or WIMPs, they must be more massive and interact even more weakly than many theoretical models predicted. Alternative theories propose that dark matter might consist of primordial black holes, tiny black holes formed in the very early universe before the first stars existed. These primordial black holes could range in mass from less than the mass of an asteroid to thousands of solar masses, and they would be extremely difficult to detect directly. However, several observations have placed limits on how much of the dark matter can consist of primordial black holes, ruling out some mass ranges while leaving others open. Another possibility is that dark matter consists of axions, hypothetical particles predicted by theories attempting to solve certain problems in particle physics. Axions would be much lighter than WIMPs, possibly billions of times lighter than electrons, but they could still account for the dark matter if they were produced in sufficient quantities in the early universe. Several experiments are now searching for evidence of axion dark matter using specialized detectors that convert axions into detectable photons in the presence of strong magnetic fields. The distribution of dark matter within the Milky Way tells us something about how galaxies form and evolve. Computer simulations of galaxy formation predict that dark matter should be distributed in a roughly spherical halo surrounding the visible galaxy, with density decreasing gradually as you move outward from the center. This predicted distribution matches observations reasonably well, but discrepancies exist that might indicate gaps in our understanding of dark matter physics or galaxy formation processes. One particularly interesting feature of the predicted dark matter distribution is the possibility of dark matter streams, coherent flows of dark matter particles moving through the galaxy along specific trajectories. These streams might be remnants of smaller dark matter halos that merged with the Milky Way billions of years ago, their particles still following similar orbits despite the tidal forces that disrupted their original structure. If dark matter streams exist, they could create localized variations in the dark matter density throughout the galaxy. Our solar system might occasionally pass through one of these streams, temporarily increasing the local dark matter density and potentially increasing the rate of dark matter interactions in detectors on Earth. Some researchers have proposed that correlations between dark matter detection experiments and the solar system's position in the galaxy might provide evidence for dark matter streams, though no convincing evidence has been found yet. The Milky Way's massive scale also affects the galaxy's magnetic field, another crucial component of the galactic environment that influences star formation, cosmic ray propagation, and the structure of the interstellar medium. The galaxy's magnetic field permeates the entire disk and extends into the halo, creating a complex three-dimensional structure that traces the spiral arms and varies in strength across different regions. The total magnetic energy stored in the Milky Way's magnetic field is enormous, comparable to the kinetic energy of all the gas in the galactic disk. This magnetic energy plays a crucial role in regulating star formation by providing support against gravitational collapse in molecular clouds. Without magnetic fields, star formation might proceed much more rapidly, consuming the galaxy's gas reservoir in a fraction of the time it has actually taken. The origin of the Milky Way's magnetic field remains somewhat mysterious. The field is probably generated and maintained through a dynamo process, where the combined effects of galactic rotation and convective motions in the interstellar medium amplify weak seed magnetic fields into the strong fields we observe today. This galactic dynamo has been operating throughout most of the galaxy's history, continuously regenerating magnetic fields that would otherwise decay over time. Cosmic rays, high-energy particles that constantly bombard Earth from space, are intimately connected to the Milky Way's mass and magnetic structure. These particles, mostly protons and atomic nuclei, are accelerated to incredible energies by shock waves from supernova explosions and other violent events throughout the galaxy. The total energy stored in cosmic rays throughout the Milky Way is comparable to the energy in starlight and magnetic fields, making cosmic rays a significant component of the galaxy's energy budget. The Milky Way's magnetic field plays a crucial role in confining these cosmic rays to the galaxy. Without magnetic fields, cosmic rays would escape into intergalactic space much more quickly, reducing the cosmic ray density throughout the galaxy. The magnetic field acts like an invisible cage, keeping cosmic rays bouncing around the galaxy for millions of years before they eventually escape. This confinement allows cosmic rays to influence the chemistry and thermodynamics of the interstellar medium, affecting star formation and the evolution of molecular clouds. The flux of cosmic rays reaching Earth is influenced by our location within the galaxy and our motion through the galactic magnetic field. As the solar system orbits the galactic center, it passes through regions with different cosmic ray densities and different magnetic field strengths. Some researchers have proposed that these variations might affect Earth's climate over long timescales, possibly even influencing the occurrence of ice ages, though the evidence for such connections remains controversial. The Milky Way's spiral structure creates additional complexity in the distribution of cosmic rays, magnetic fields, and star formation. Spiral arms are regions of enhanced density where gas clouds pile up and stars form at elevated rates. These regions also contain more supernovae, the primary source of cosmic rays, leading to higher cosmic ray production rates in spiral arms compared to the regions between arms. Our solar system's periodic passages through spiral arms might expose Earth to elevated cosmic ray fluxes, potentially increasing the rate of mutations in living organisms and affecting climate through changes in cloud formation. Some studies have suggested correlations between mass extinction events in Earth's history and the timing of spiral arm passages, but these correlations remain uncertain, and the physical mechanisms that might connect spiral arm passages to extinctions are not well established. The mass of stars in the Milky Way represents only about 5 to 10% of the galaxy's total mass, but these stars are responsible for most of the light we see and play crucial roles in the galaxy's chemical and dynamical evolution. The 200 to 400 billion stars in the Milky Way span an enormous range of masses, from tiny red dwarfs less than 1/10 the mass of the Sun to massive blue supergiants more than 100 times the Sun's mass. This stellar mass distribution follows a pattern called the initial mass function, which describes how many stars form in different mass ranges. The initial mass function is heavily skewed toward low-mass stars, with far more red dwarfs than Sun-like stars and far more Sun-like stars than massive stars. This distribution means that most of the galaxy's stars are small, dim red dwarfs that contribute relatively little to the total starlight, but contain a significant fraction of the stellar mass. The most massive stars, despite being rare, have an outsized influence on galactic evolution. These stellar giants live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae. These explosions scatter heavy elements into the interstellar medium, enriching the gas from which future stars will form. The energy released by supernova explosions also drives turbulence in the interstellar medium and can trigger or suppress star formation in nearby molecular clouds. The cumulative effect of billions of years of stellar evolution has transformed the chemical composition of the Milky Way. The first generation of stars formed from nearly pure hydrogen and helium, but subsequent generations incorporated increasing amounts of heavy elements produced by their predecessors. Today, stars forming in the galactic disk contain about 2% heavy elements by mass, a dramatic increase that has enabled the formation of rocky planets and the complex chemistry necessary for life. The study of stellar populations in the Milky Way provides a detailed history of the galaxy's chemical evolution. By measuring the chemical compositions of stars with different ages, astronomers can reconstruct how the abundance of various elements has changed over time. These studies reveal that different chemical elements are produced by different stellar processes, with some elements like carbon and oxygen being produced primarily in massive star supernovae, while others like iron come from both massive stars and white dwarf supernovae. The distribution of elements throughout the galaxy isn't uniform. Stars near the galactic center tend to be more metal-rich than stars in the outer disk, reflecting higher star formation rates and more efficient chemical enrichment in the inner galaxy. This metallicity gradient provides clues about how gas flows throughout the galactic disk and how efficiently different regions of the galaxy mix their chemical enrichments. Vertical gradients in chemical composition also exist, with stars farther from the galactic plane tending to be more metal-poor than stars in the disk. This vertical gradient reflects the different formation histories of the thin and thick disk components, with the thick disk containing older, more metal-poor stars that formed earlier in the galaxy's history. The gas content of the Milky Way, while representing only about 10 to 15% of the galaxy's total mass, plays a crucial role in ongoing star formation and future evolution. This gas exists in multiple phases with vastly different physical properties, from cold molecular clouds with temperatures of just 10 to 20 degrees above absolute zero to hot ionized gas with temperatures exceeding 1,000,000 degrees. The cold molecular gas, primarily consisting of molecular hydrogen, H2, represents the immediate fuel for star formation. This gas is concentrated in massive molecular clouds scattered throughout the galactic disk, with the largest complexes containing millions of solar masses of material. These giant molecular clouds are the birthplaces of stars, regions where gravity overcomes magnetic pressure and turbulent support to trigger the collapse of dense cores into protostars. The distribution of molecular gas throughout the Milky Way follows the spiral arm pattern, with higher concentrations in the spiral arms where density waves compress the gas and trigger cloud formation. The central regions of the galaxy contain the central molecular zone, a concentration of molecular gas containing tens of millions of solar masses within just a few hundred light-years of the galactic center. This gas exists in an extreme environment with high temperatures, pressures, and magnetic field strengths that make star formation proceed differently than in the galactic disk. Atomic hydrogen gas, HI, represents another major component of the galaxy's gas content. This gas exists at somewhat higher temperatures than molecular hydrogen, typically around 100 degrees Kelvin, and extends to larger distances from the galactic plane. The HI gas forms a disk that extends beyond the visible stellar disk, reaching distances of 60,000 to 80,000 light-years from the galactic center. This extended gas disk provides evidence for the dark matter halo, as the rotation velocities of the gas at these large distances can only be explained by the presence of significant amounts of invisible mass. The hot ionized gas phase, while contributing relatively little mass, plays an important role in the galaxy's energy budget and the cycling of matter between different phases. This hot gas exists primarily in the galactic halo, heated to millions of degrees by supernova explosions and stellar winds. The total mass of hot gas in the halo might be comparable to the cold gas in the disk. Though measuring this hot component is challenging because it emits primarily in X-rays and can be difficult to distinguish from foreground emission in Earth's own hot halo. The cycling of gas between these different phases, from cold molecular clouds to hot ionized gas and back again, represents a fundamental process in galactic evolution. Stars form from cold molecular gas, then return material to the interstellar medium through stellar winds and supernova explosions. This returned material is often heated to high temperatures before eventually cooling and condensing into new molecular clouds, where the cycle can repeat. This galactic fountain process operates continuously throughout the disk, with hot gas rising into the halo before cooling and falling back down to form new generations of stars. The timescale for this cycling is approximately 100 million to 1 billion years, meaning that the gas in the Milky Way has been cycled through stars multiple times over the galaxy's history. Each cycle increases the heavy element content of the gas, gradually enriching the interstellar medium with the products of stellar nucleosynthesis. The Milky Way's mass also determines the galaxy's ability to accrete fresh gas from the intergalactic medium. Computer simulations suggest that galaxies like the Milky Way continue to accrete gas throughout their lifetimes, pulling in material from the surrounding cosmic web along dark matter filaments. This ongoing gas accretion replenishes the gas consumed by star formation, allowing the galaxy to maintain steady star formation rates over billions of years. Recent observations have detected signatures of this gas accretion in the form of high-velocity clouds, concentrations of neutral hydrogen moving at velocities inconsistent with simple galactic rotation. Some of these clouds are probably falling into the Milky Way for the first time, carrying fresh gas that has never been processed through stars. Other high-velocity clouds might be gas ejected from the galactic disk by supernova-driven outflows that is now falling back down, representing the return flow of the galactic fountain. The total rate of gas accretion onto the Milky Way remains uncertain, with estimates ranging from less than 1 solar mass per year to several solar masses per year. This uncertainty reflects the difficulty of detecting diffuse gas in the galactic halo and distinguishing infalling gas from other components of the galactic gas distribution. Future observations with more sensitive radio telescopes should help constrain the accretion rate and determine whether the Milky Way's gas reservoir is growing, shrinking, or remaining roughly constant. The stellar kinematics of the Milky Way, the motions of stars throughout the galaxy, provide crucial information about the galaxy's mass distribution and dynamical state. Stars in the disk orbit the galactic center in roughly circular paths, with velocities that vary systematically with distance from the center. This rotation curve encodes information about the total mass distribution, allowing astronomers to measure the galaxy's mass profile from the center out to the edge of the observable stellar disk. But not all stars follow circular orbits. Many stars have elliptical orbits that carry them closer to and farther from the galactic center during each orbit. The degree of orbital ellipticity varies among different stellar populations, with older stars tending to have more eccentric orbits than younger stars. This velocity dispersion, the spread in stellar velocities at any given location in the galaxy, provides information about the age and formation history of different stellar populations. The thick disk stars, in particular, show higher velocity dispersions than thin disk stars, indicating that they formed through more violent processes or have been dynamically heated over time. Some thick disk stars might have formed during early merger events when the galaxy was still assembling itself, while others might have been scattered into their current orbits by gravitational interactions with massive molecular clouds or with the central bar structure. The discovery of the Milky Way's central bar, an elongated structure extending several thousand light-years from the galactic center, has important implications for understanding the galaxy's dynamics and mass distribution. This bar, oriented at an angle to the line connecting the Sun and galactic center, affects the orbits of stars and gas clouds throughout the inner galaxy. The bar's gravitational influence creates regions where gas piles up and regions where it's evacuated, helping to channel gas toward the galactic center and influencing the rate of star formation in the inner galaxy. The existence of the bar also affects measurements of the galaxy's mass distribution. The bar's elongated shape creates a non-axis symmetric gravitational potential that must be accounted for when interpreting stellar kinematics in the inner galaxy. Failure to account for the bar can lead to systematic errors in mass estimates derived from rotation curve measurements. The vertical structure of the Milky Way provides another dimension for understanding the galaxy's mass distribution. Stars in the disk have a vertical distribution that can be approximated by an exponential decline in density with height above the disk. The scale height of this distribution varies for different stellar populations, with younger stars confined closer to the midplane and older stars having larger scale heights. This vertical distribution is maintained by a balance between the gravitational pull toward the disk midplane and the vertical velocity dispersion of stars. Measuring the vertical density distribution and velocity dispersion allows astronomers to estimate the total surface density of matter near the Sun's position in the galaxy. These local measurements provide important constraints on the amount of dark matter in the disk, though debate continues about whether significant amounts of dark matter exist in the disk or whether it's confined primarily to the halo. The Milky Way's globular cluster system provides unique probes of the galaxy's gravitational potential at large distances. These dense stellar systems, each containing hundreds of thousands to millions of stars packed into spherical regions just tens of light years across, orbit throughout the galactic halo at distances ranging from a few thousand to over 300,000 light-years from the galactic center. The orbital properties of globular clusters reflect the total mass distribution of the galaxy. Clusters with large orbital radii sample the gravitational potential at great distances where dark matter dominates the mass budget. By measuring the positions and velocities of many globular clusters and modeling their orbital dynamics, astronomers can estimate the total mass of the galaxy extending far beyond the visible disk. The Milky Way contains approximately 150 to 160 known globular clusters, though the total population might be somewhat larger if we account for clusters that have been destroyed by tidal forces or are hidden behind obscuring dust in the galactic plane. These clusters fall into distinct populations with different metallicities and spatial distributions, reflecting different formation epochs or different origins. The metal-poor globular clusters containing stars with very low heavy element abundances are distributed in a roughly spherical halo around the galaxy and probably formed very early in the Milky Way's history. The metal-rich globular clusters have a more flattened distribution and might have formed later, possibly in association with the thick disk component. Some globular clusters show chemical anomalies that suggest they might not have formed in the Milky Way at all. These clusters have stellar populations with unusual element abundance patterns that don't match what we see in Milky Way field stars. These anomalous clusters might have formed in dwarf galaxies that were later captured and disrupted by the Milky Way, with the clusters surviving as the only remnant of their destroyed parent galaxies. The study of stellar streams in the Milky Way's halo has revolutionized our understanding of the galaxy's assembly history. These streams, thin rivers of stars stretching across the sky, represent the tidal debris from satellite galaxies and globular clusters that have been torn apart by the Milky Way's gravity. Each stream traces an orbit through the galaxy, and by mapping these orbits, astronomers can reconstruct the trajectories of the disrupted objects and learn about the galaxy's gravitational potential. The Sagittarius stream, the most prominent stellar stream in the sky, wraps completely around the Milky Way multiple times, creating a complex three-dimensional structure that has been traced using data from large stellar surveys. This stream represents the ongoing destruction of the Sagittarius dwarf elliptical galaxy, a small galaxy containing several billion stars that is currently passing through the galactic disk and will eventually be completely incorporated into the Milky Way. Dozens of other stellar streams have been discovered in recent years, each representing a destroyed satellite galaxy or disrupted globular cluster. These streams provide detailed information about the galaxy's gravitational potential and its time evolution. Any variations in the galaxy's mass distribution over time, such as the growth of the central bar or changes in the dark matter halo shape, would affect the structure of these streams in detectable ways. The streams also provide evidence for dark matter substructure in the galactic halo. If the dark matter halo contains numerous small dark matter clumps, as predicted by standard cosmological models, these clumps would gravitationally perturb stellar streams as they pass by, creating detectable gaps and density variations in the streams. Searches for such perturbations are ongoing, with some tentative evidence for dark matter substructure, though definitive detections remain elusive. The Milky Way's satellite galaxies provide another crucial probe of the galaxy's mass and dark matter distribution. These small galaxies, ranging from tiny ultra-faint dwarfs containing only a few thousand stars to larger irregular galaxies like the Magellanic Clouds, orbit within the Milky Way's dark matter halo and trace its gravitational potential at various distances. The number of satellite galaxies and their spatial distribution provide tests of cosmological models and dark matter physics. Standard dark matter models predict that massive galaxies like the Milky Way should be surrounded by thousands of dark matter subhalos, most of which wouldn't contain any stars. Some of these subhalos should have captured enough gas to form stars, becoming visible as dwarf galaxies. Observations reveal approximately 60 known satellite galaxies around the Milky Way, far fewer than the thousands of dark subhalos predicted by models. This discrepancy has been called the missing satellites problem and has motivated extensive searches for ultra-faint dwarf galaxies that might have been missed in earlier surveys. These searches have been remarkably successful, discovering dozens of new satellites in the past decade, but it remains unclear whether the total number of satellites will match theoretical predictions. The satellite galaxies themselves contain significant amounts of dark matter. The dwarf spheroidal galaxies, in particular, appear to be the most dark matter-dominated systems known, with mass-to-light ratios indicating that dark matter outweighs normal matter by factors of hundreds or even thousands. These galaxies move much faster than their stellar content alone could explain, requiring large amounts of invisible mass to keep them gravitationally bound. The extreme dark matter content of these small galaxies makes them excellent laboratories for studying dark matter properties. The distribution of dark matter within these systems provides clues about dark matter particle physics, particularly whether dark matter particles can interact with each other through forces beyond gravity. If dark matter self-interacts, it would affect the internal structure of these dwarf galaxies in potentially observable ways. The ongoing tidal disruption of satellite galaxies by the Milky Way's gravity contributes to the galaxy's growth and evolution. Each consumed satellite adds its stars, gas, and dark matter to the host galaxy, incrementally increasing the Milky Way's mass. This hierarchical assembly process, where larger structures form through the merger of smaller ones, is a fundamental prediction of cosmological models and appears to match what we observe in the Milky Way's halo. The chemical compositions of stars in the galactic halo provide a fossil record of this assembly process. Different satellites had different chemical enrichment histories before being consumed, so their stars carry distinct chemical signatures that can be detected today. By identifying groups of stars with similar unusual chemical patterns, astronomers can identify the remnants of ancient merger events and reconstruct when these events occurred. Recent analyses of Gaia data, combined with chemical measurements from large spectroscopic surveys, have revealed that a significant fraction of halo stars, perhaps 30 to 50%, came from a single massive merger event approximately 10 billion years ago. This event, sometimes called the Gaia-Enceladus merger, involved a substantial satellite galaxy containing billions of stars that collided with the Milky Way when our galaxy was much younger. The stars from this ancient collision are now scattered throughout the inner halo, still following similar orbital patterns that betray their common origin. Understanding the mass that was delivered to the Milky Way through such mergers helps constrain models of galaxy assembly and the growth of massive galaxies over cosmic time. Each merger event adds mass, triggers star formation, and can reshape the galaxy's structure, leaving imprints that persist for billions of years and can be detected through careful study of stellar kinematics and chemical compositions. The future evolution of the Milky Way's mass will be dominated by the approaching collision with Andromeda. Computer simulations of this future merger have revealed what we can expect over the next several billion years. The galaxies will make their first close pass in approximately 4 billion years, with their disks potentially colliding and passing through each other. This first encounter will scatter stars and trigger intense bursts of star formation as gas clouds collide. The two galaxies won't merge immediately, but will separate again after this first pass, perhaps moving apart by hundreds of thousands of light years before gravity pulls them back together for a second encounter. Each close pass will extract more orbital energy through tidal interactions and dynamical friction, gradually bringing the galaxies closer together. After several orbits over a period of perhaps 1 to 2 billion years, the two galaxies will finally merge completely, their stars and dark matter halos combining into a single massive elliptical galaxy. The final merged galaxy will have a mass of approximately 2 trillion solar masses, making it one of the largest galaxies in the local universe. This mass will be dominated by dark matter, as in the present-day galaxies, but the distribution of that dark matter might be different. The merger will likely scatter some dark matter to large distances, creating an extended dark matter halo around the merged system. During the merger, the supermassive black holes at the centers of the Milky Way and Andromeda will sink toward the center of the merged galaxy through a process called dynamical friction. As they move through the stellar background, their gravitational influence accelerates nearby stars, extracting energy from the black hole's orbital motion and causing them to spiral inward. Eventually, the two supermassive black holes will merge, creating a single black hole with a mass of about 50 million solar masses and releasing tremendous amounts of energy in the form of gravitational waves. These gravitational waves from the black hole merger will carry away a significant fraction of the merged black hole's mass energy, perhaps equivalent to a few million solar masses converted directly into gravitational radiation. This energy release will dwarf the output of all the stars in both galaxies combined, though it will occur on such short timescales that no individual star or planet will be significantly affected. The gravitational waves will propagate through the universe at the speed of light, eventually reaching distant galaxy clusters billions of light years away. The mass of the Milky Way, when viewed in the context of cosmic evolution, represents a snapshot of an ongoing process that began shortly after the Big Bang and will continue for trillions of years into the future. The galaxy started as a small overdensity in the dark matter distribution of the early universe, a region where dark matter was slightly more concentrated than average. Over time, This overdensity grew through gravitational instability, attracting more dark matter and eventually pulling in the first gas that would form the first stars. This early growth phase occurred rapidly on cosmic timescales, with the first significant dark matter halos forming within a few 100 million years after the Big Bang. The Milky Way's earliest stellar populations probably formed when the universe was less than 1 billion years old, in small proto-galactic fragments that would later merge to build the main galaxy. These early star formation events occurred in an environment very different from today's galaxy, with almost no heavy elements and intense radiation from the first generation of massive stars. As the galaxy grew through mergers and gas accretion, it developed the structures we see today: the central bulge, the stellar disk, the spiral arms, and the extended dark matter halo. Each of these components formed through different processes and at different times, creating the complex multi-component structure we observe in the present-day Milky Way. The total mass that has passed through the Milky Way over its lifetime exceeds the current mass by a significant factor. Gas has been accreted, converted into stars, and then expelled back into intergalactic space through powerful winds driven by supernova explosions. Some estimates suggest that the Milky Way might have expelled as much mass as it currently contains, meaning the lifetime integrated mass of the galaxy could be twice its current mass or more. This mass loss through galactic winds represents an important feedback mechanism that regulates galaxy growth. Without these winds, galaxies would convert their gas into stars much more efficiently, producing more massive galaxies than we observe. The energy from supernova explosions and stellar winds drives material out of the galaxy, some of which might eventually fall back, while some escapes into the intergalactic medium permanently. The Milky Way's massive scale places it among the largest galaxies in the local universe, but not among the very largest. Giant elliptical galaxies in the centers of massive galaxy clusters can contain 10 to 100 times the Milky Way's stellar mass, making them true galactic titans. These massive galaxies form through extensive mergers of many smaller galaxies, assembling their enormous masses over billions of years of galactic cannibalism. However, when we account for dark matter, the mass hierarchy changes somewhat. While giant elliptical galaxies contain more stars than the Milky Way, their total masses, including dark matter, might be only a few times larger. The dark matter halo masses of galaxies don't scale linearly with stellar mass, and processes like tidal stripping in cluster environments can remove dark matter from galaxies, complicating the relationship between stellar and total mass. The Milky Way's role in the cosmic matter budget is significant when we consider that there are hundreds of billions of galaxies in the observable universe. If we multiply the Milky Way's mass by the number of similar galaxies, we can estimate the total mass contained in galaxy mass dark matter halos throughout the cosmos. This mass represents a substantial fraction of all the matter in the universe, though most of the universe's mass resides in larger structures like galaxy clusters and the cosmic web itself. Looking to the far future, the ultimate fate of the Milky Way's mass depends on the cosmological constant and the future evolution of the universe. Current observations suggest that the universe will continue expanding forever, accelerating due to dark energy. In this scenario, the merged Milky galaxy will become increasingly isolated as cosmic expansion carries other galaxy groups beyond our cosmic horizon. Over timescales of trillions of years, the stars in Milkomeda will gradually die, converting the galaxy's stellar mass into white dwarfs, neutron stars, and black holes. Star formation will cease as the gas supply is exhausted and no new gas accretes from an increasingly empty intergalactic medium. The galaxy will slowly fade, transforming from a bright spiral into a dark collection of stellar remnants and unbound gas. On even longer timescales, approaching a Google years, The black holes themselves will evaporate through Hawking radiation, converting their mass into elementary particles and radiation. Eventually, the mass that once formed the Milky Way will be dispersed across a vast volume of space, diluted to the point where the matter density approaches zero. But that ultimate fate lies incomprehensibly far in the future. For now, and for billions of years to come, the Milky Way remains a massive, dynamic, evolving structure, a cosmic metropolis containing hundreds of billions of stars and trillions of planets, all bound together by gravity and evolving according to physical laws we are only beginning to understand fully. I wish you a very good night. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering, and remember that you're part of a trillion solar mass galaxy, a massive cosmic structure that has been growing and evolving for over 13 billion years and will continue to shape the universe around it for billions of years to come. This is Boring Space signing off. Cheers.